Hi, I am Arib. You are watching my YouTube channel. Under frequency protection relays. As the world transitions to distributed energy resources and renewable generation, frequency protection has become a commonly specified technique for reliable asset integration. Frequency protection monitors the power system frequency and signals when the frequency departs from normal. In this article, we explore what normal frequency is, what scenarios cause power system frequency to vary, and some of the common protection elements which act on these fault scenarios. Power system frequency. Following the famous disagreements between Edison and Westinghouse in the early days of electrical engineering, the victor of the debate between alternating current AC and direct current DC was the former. Alternating current is a constantly varying magnitude of current over time, while DC is constant. While beyond the scope of this article, AC has advantages in electromagnetic induction, which allowed technologies such as transformers to scale and transport bulk energy, while HVDC is a viable alternative today. The vast majority of power transmission and distribution is AC. When frequency is discussed in a power system context, it is the cycles per second of the electrical current. For most transmission and distribution, it is either 50 Hz or 60 Hz, although some rail applications use lower frequencies. What scenarios cause power system frequency to vary? Frequency is a fundamental quantity in the design of an AC electrical network. All equipment selected must be designed to operate at this frequency, and in a healthy system, there should be very little movement. The frequency of an electricity network is generally governed by the synchronous generators in conventional power plants. These massive machines generate power at a specified frequency. At a steady state, at rated power, the frequency should not vary. When the power demanded of generator changes, we can start to see variations in frequency. The power system inertia, or stored energy, will attempt to maintain the frequency output under higher load. A simple analogy is the behavior of a car when driving at a constant speed, say 50 km per hour. The car's engine rotates at a specific RPM. RPM is a form of frequency. When that car reaches an inclined hill, more power output is needed to achieve the same speed. When this happens, the RPM will start to fall, as the engine is placed under more load. This is frequency falling when the power output is the same. If you can increase the power output, the car avoids stalling. If you can't, the car stalls. In our power system example, if our generator can't match the load, the generator stalls, and the power goes out. Same to when the car reaches a decline hill. In this case, less power output is needed to maintain the same speed. If you did not reduce your accelerator application, the RPM and car speed would increase at the same power output. In this case, the generator is exceeding the demand, and the frequency would increase if the power generation remained the same. This is why frequency is a useful protection metric. It allows us to see if the generation and load is balanced and allows protection engineers to intervene if this mismatch becomes an issue. Why is frequency protection being more commonly used? The main reason is the adoption of distributed generation. Generators need protection against frequency events, and these connections need frequency protection. Furthermore, these distributed generators often use asynchronous generation, such as power inverters in solar power plants. With no mechanical inertia behind them, these generation sites have less capacity to respond to fluctuations in power system frequency without disconnection. Conclusion: all these frequency features are available in NOJA Power's OSM recloser system, and many generation sites will use a combination of them. Likewise, Any network that wishes to implement an automatic load shading scheme can do so with NOJA Power OSM reclosers. This design can help avoid blackouts under generation shortfalls, improving the power system performance and reliability of power.